Hello and welcome to Modern Thatch Living. What I'd like to do today is talk about the air source heat pumps again. The original video that I did on this has been quite popular and it's raised quite a few questions from viewers. So what I'd like to do today is try and address some of those questions, which were primarily around the cost of running a system like this, and talk to you about how we've optimized the system and what we find with our system as it's set up now. In the last week, we've had some very cold weather. It's typically been about -9 at night and around, well, it's been struggling to get above -2 during the day. So it's been quite a good time to see how the system is performing and what sort of temperatures we get around the house. Anyway, I hope you find this interesting, and we'll talk about these things in the rest of the video. So when optimizing the system, what we're trying to do is minimize the temperature of the water circulating through the system, but still maintaining a temperature that's comfortable to work in. Now, the room that we're in now is actually very important because this is where Nuala does all her work. She sits very stationary at that desk and works on a computer all week. And so for that to be a comfortable place to work, we have to keep the temperature at about 20-21 degrees in here. Now, this is quite a challenging room and it makes a good baseline room to work from. It's got 3 outside walls and it's got lots of glass. And so there is actually a lot of heat loss from this room. And when it was -5 outside during the day, it was actually very difficult to get the temperature above 19.5 with the flow settings that I've picked. Now, I could have increased the flow temperature, but then that would have become very costly. And Nuala agreed that the temperature in the room was comfortable enough to actually work in during that period. Normally this room is kept at about 20-21 degrees and the radiator valves are always on in this room, and they're set to about 24 degrees. But we would never achieve that because the flow temperature is much lower than the one that would allow you to get to that point. This isn't the hardest room to heat in the house, and I'll show you the hardest room in a bit. That room we have to have a different strategy, but we don't use that all the time. It's more of a social living room area, and so during the day is not actually usually being used unless we've got visitors at a weekend. So this room is very large and it's an old building, so it's thermally very inefficient and has a large volume of air to heat up. Fortunately, there is a log fire in here. Without the log fire and with the flow temperature that we use, and if it was -5 outside, we can only achieve a temperature of about 16 degrees in here. With the log fire, we can achieve a temperature of about 20-21 degrees quite easily. Unfortunately, we have a good supply of wood on site, so that we can keep this going as long as we need it. To heat this room, we have a fan coiled unit, which I can show you. So this fan coiled unit is sufficient to heat the whole room. It's got 22mm pipe that runs into it, and a series of fans in there that blow air across a heat exchanger up into the room. It's amazingly efficient, and with a high enough flow temperature for the conditions outside, it is actually very effective at heating this room up. However, it would be very easy to spend a lot of money on heating using this without the log fire. So when thinking about the efficiency of an air source heat pump and the costs associated with it, I've tried to think about a way that would allow me to give you information which would be useful to assess yourselves whether this is something that you might be interested in. Now, it isn't very useful for me to just tell you about the cost of running this house, because the size of the house matters, the amount of insulation matters, and the way you run the system matters a lot. And so what I'm going to try and do is use our setup to illustrate the sort of costs involved and how they might compare with oil. So when talking about air source heat pump efficiencies, it's quite useful to talk about the coefficient of performance, or COP. Now, what the COP represents is, for example, a value or a COP value of 4 means that if you put in 100 units of energy, you'll get 400 units of energy out of the air source heat pump. Now, the COP value varies with outside air temperature, because fundamentally you're extracting heat from the air around the heat pump. And it also varies with the temperature, the flow temperature that you're using to circulate the energy around your house. So what you can do is, with some manufacturers, is you can actually find graphs that describe the COP value against the outside temperature and different flow temperatures, and typically they use about 35 degrees or 55 degrees or 65 degrees for the flow temperatures, and illustrate all three. So for the system that we use, the COP table or graph looks like this. What you can see in this graph is the COP plotted on the y-axis and the outside temperature plotted on the x-axis. Shown here are 3 different flow temperatures, 35, 45 and 55 degrees C. As you can see, when you go to lower flow temperatures, the system becomes more efficient with a higher COP for a given outside temperature. Using this graph, I aim to get a flow temperature of 28 degrees at an outside temperature of -2. So the system that we've got has a predictive curve that allows the system to calculate the flow temperature based on the outside temperature. And you can adjust the slope of that predictive curve and the offset to balance the system to suit the house. The system that we've got also has the ability for you to program in your own predictive curve if you want to. It's not something that I felt necessary to do at the minute, but might make the long-term running easier if I do decide to do that, because I would have to monitor the system less than I do at the minute. Currently, I keep a very close eye on the flow temperature and the temperature within the house, because it would be very easy to find that your flow temperature is much higher than you need, and you're actually spending a lot more money than you need to achieve a warm house. I'm aware that on some systems the predictive curves and control of flow temperature are potentially behind a series of controls that only the installer can access. I would actually find that very annoying in that situation, and if I had a system like that, I would demand actually having the password to be able to access these features myself. I think it's highly unlikely that an installer will spend the time and effort needed to optimize for your particular house. And I think that it actually requires quite a lot of input from the user to get this right. I think when installers install on systems that the user can't access, what they're doing is making a compromise and assuming that that will be okay for you. And so when the temperatures drop outside, you may find that you're actually spending more than you need to. But if you can't access the controls, you've got no way of altering that yourself. The system that we've got allows the user full access, but it does have warnings around some of the parameters that you shouldn't change them and that only the installers should change certain parameters. And I totally accept that. There are some things I just don't want to be touching. But the flow temperature and the predictive curve that controls that flow temperature, I think, are really important parameters for the user to be able to access. So if you've got a system like this, I would highly recommend you find out how you change these and whether you can on your system without having a password to get onto it. If you do need to get access, then I would actually demand from your installer to have the passwords to allow you to change these parameters. So anyway, enough of that. So as an illustration of how expensive this can be, last week when the temperatures dropped down to -9, I noticed that the flow temperatures were actually a lot higher than I would normally run the system at. So I went and adjusted the flow temperature, as you can see here, and the house remained comfortable, but it actually works out at about £11 cheaper a day to run at this new flow rate. So it had a very big impact, and if I couldn't access the controls, I wouldn't have been able to make that change. So if we're looking at the cost of running the system, there are some parameters which I know, and there are some parameters which I've had to make some assumptions about. So obviously the cost of electricity, I know what that is. For us at the minute, it's 32 pence a unit. The price of oil, I've looked up, and currently the price range is 82.5 pence per litre up to 98 pence per litre. So I've decided for the calculations that I'm doing here to take the value of 82.5 because that's the cheapest I could find, and that's what I would buy if I was buying oil at the minute to compare. Then there's boiler efficiency. So if you're looking at boiler efficiencies of modern combi boilers, you can find values of 93, 95%. I suspect that with a system that's installed and has been running for a little while, you probably don't achieve those sorts of efficiencies. So I've gone with an efficiency of about 90%. And I know that will outrage some of the viewers, but I suspect that a lot of people are running boilers that do not have the optimized efficiency that you get in a factory setting. And I would say to those viewers that find this outrageous, I am picking the lowest price of oil that I can find. And I think 82.5 pence a litre is actually pretty good at the minute. So with those parameters and a flow temperature of about 28 degrees, then when the outside air temperature is about naught, the cost of electricity has parity with the cost that it would be to heat the house with oil. So it means that if the air temperature is less than 0, we will actually be spending more on electricity than we do on oil. Whereas if we have an air temperature outside which is higher than 0, then the cost of heating the house using the air source heat pumps is better than the cost of heating the house with a very efficient oil boiler. The reality is, where we live, the air temperature most of the time is above 0. So at the minute, it makes sense for us to heat the house with our air source heat pumps. However, all of these calculations change depending on the price of electricity and the price of oil. If we were to take the highest price of oil that I found, then the system would actually have parity with oil at a temperature of about -2 to 0. So a little bit better. If the price of electricity in April 2023 goes up by 20%, as it's predicted to, and so our price per unit here goes up to 38 pence per unit, and if the price of oil doesn't increase in that time either and stays at the cheaper rate of 82.5 pence per litre, then for parity between oil and the air source heat pumps to occur, we would need air temperatures outside of about 5 degrees. Now, obviously, at that point, it becomes questionable if you were just installing an air source heat pump purely on the basis of trying to save money. It wouldn't be worse, but it wouldn't be better. You would have to be doing it for environmental reasons. However, if the cheapest oil at that point you can buy is closer to 96 pence per litre, then the performance of the air source heat pump will still be better when the air temperature is above 2 degrees than the performance of an oil-fired system. And currently where we live, the air temperature is such that for most of the time it is actually in the region of 2 to 5 degrees. And so it would still be worthwhile under those conditions having an air source heat pump for economic reasons. In the longer term, for us, we plan to have solar panels outside, and of course that changes the calculations completely, because it would essentially be driving the apparent unit cost of electricity down for us. But there isn't a clear answer to whether this is a good thing to do or not if the price of electricity goes up and the cost of oil doesn't change. So are there any issues running the heat pumps at these lower temperatures, these low flow temperatures? Well, normally we don't have an issue. However, at -9, we did start to get issues with the system icing up and not being able to de-ice properly or adequately enough. So what happens with air source heat pumps is that because they are essentially refrigerators working in reverse, you get ice forming on the heat exchanger at the back. So every so often, what the system does is it reverses the flow and sends warm water back into the heat exchanger to melt the ice. I think the problem was that when the air temperature outside was -9, the flow temperature of the water in the system being fed back into the heat exchanger wasn't high enough to actually melt the ice sufficiently and allow the water to drain away quickly enough before reforming into ice. My solution to that was actually to turn the flow temperature up for a bit, and that cleared the system and we started to operate more efficiently under those circumstances. So the other thing that we saw happening relates to the noise from the air source heat pumps. Now, people get very exercised about this and they seem to have a real thing about heat source pumps being noisy. Well, our heat source pumps emit, when they're at maximum, 40 decibels. And as a comparison, that's not very different to a modern, new oil-fired boiler, which would be in the 40 to 45 decibel range. However, an air source heat pump emits 40 decibels when it's working maximally. And actually, they very rarely, in our case, work at their maximum fan speed. The other thing is that they aren't on continuously. They're on quite a lot of the time, but they're also switching off quite a lot of the time. So just like an oil boiler, although we have the water circulating at a continuous flow temperature around the house, that doesn't actually mean the air source heat pumps are on all the time, except when it's really cold outside. So the other thing that happened with the lower flow temperatures was that we got some ice build up on one of the fans, and that made the fan blades imbalanced and developed a bit of a wobble, and they started to bang on the side of the unit. Not very much, but just enough to be annoying. So actually the solution to that was very simple. I took a watering can out, small watering can out with water in it that was about 50 degrees. And when the fan was in a defrost cycle and had stopped, I then poured a small amount of water onto the blades. It melted the ice off, and then the unit was quiet again. Well, I hope that you found this discussion helpful. It's not an easy calculation to figure out whether it's worth doing or not. If you were living somewhere very cold and the electricity prices are high and the cost of oil is low, then it is a no-brainer. The oil would be better for you in terms of the financial cost. Certainly in the south of the UK, I think so long as the electricity prices don't go up too much more than the price of oil rises, then having an air source heat pump does seem to be very effective if you run it efficiently. But it does require a lot of effort and monitoring to actually run an air source heat pump as efficiently as you can. So anyway, I hope that you've found that useful, and I look forward to seeing you in the future. Goodbye.